As a neurosurgeon, for the last 10 years, I've been telling young people that they're paralyzed from their accident, and walking, for many of them, would be very unlikely. When people ask me about a cure for paralysis, my answer recently has changed. Today I say, it's not a matter of if, it's a matter of when.
You dream about that situation when you're going to play college football, I think. You dream about playing the #1 team in the nation. Alabama was that. We're coming down to about 5 minutes left in the first half. Scores 3-0, Alabama, and we're moving the football. We're down to about the Alabama 35, and play comes in from the bench, and they called a sweep play to me. And all of a sudden, I felt a jolt from the back. Came down head first on artificial turf. I can feel it right now. Just thinking back, I can see laying on the field and looking up and still feel what I felt at that moment. That was nothing. I just didn't feel anything. But, I had no idea what was wrong with me. I really had never thought about breaking my neck playing football.
Kent Waldrop, 1974 All-American Texas Christian University star running back, has not played football since that day. His injury has left him paralyzed. Today in the United States, there are at least 250,000 people who, like Kent, have been paralyzed from spinal cord injury. Every year, 15,000 more will join the ranks, either from a motor vehicle accident, sporting accident, a fall, or even a gunshot wound. Each story is tragic and usually leaves the victims bound to a wheelchair for the rest of their lives. Until recently, a possible cure for an injury to the spinal cord was unheard of. But now, within the field of neuroscience, a revolution is taking place. In basic research, scientists are challenging medical dogma that spinal cord injuries must be permanent. On the front line of clinical treatment, doctors are introducing aggressive new programs to minimize the effects of paralysis. And using the latest advances in technology, biomedical engineers and computer scientists are making the idea of the bionic woman a reality. The journey between the latest technology and earlier ones has been long in coming. Before World War II, a person with spinal cord injury had very little chance of survival. Since then, centers like Stoke Mandeville in Great Britain have pioneered ways to help people live with their injuries. Their philosophy is that with physical therapy and an acceptance of their situation, patients can look forward to a normal lifespan. It's here that people like Gary Byrne must begin to contemplate a future quite different from the one he'd hoped and planned for. Gary was on vacation when he fractured his spinal column. It was a hot day, and he and his two friends had stopped into a pub for a drink. When they came out, the sea looked tempting, and Gary dove into shallow water.
I tried to dive out pretty far because it was fairly shallow at near where we was. And when I went in the water and I went my hands and my legs to swim back up, I didn't have any. I was pretty terrified, actually. I thought I was going to drown. I thought, will they realise that I'm underneath the water? Will they come and get me out? And I was underneath there a pretty long time. I started to get a bit worried about it because I was swallowing water.
We thought he was just messing around because he was floating on top of the water, moving his head from side to side. Then we realised there was something wrong when there was blood. Blood appeared from his head.
Next thing I remember, I was in the hospital.
We were both stunned, weren't we?
Yeah, we went down there and the nurse said, go in and try and cheer him up. I found it totally impossible. I couldn't talk to him.
He was just lying there, helpless. And he recognised who we were, although his speech was very slurry. And the first thing he said to me was, "What kept you?"
There was a sister the night after we'd seen the doctor, when Gary had been taken out of intensive care, been taken down to one of the wards, And she said to us, had we seen the doctor? And I said, yes. She said, oh, well, you know then that Gary will never walk again. Well, the doctor hadn't actually told us this.
What did you say?
Well, I couldn't say anything. I was too shocked.
Gary has weights attached to his head to relieve the pressure on the spine and to allow the bones to realign themselves. The higher the injury to the spinal cord, the more extensive the paralysis. Gary's fracture is just below his neck. Continual passive physical therapy keeps his joints flexible and his tendons from shrinking. Every 3 hours, his body will be turned to prevent bed sores. It is this high standard of nursing care that keeps Gary and thousands like him alive today. But the likelihood of a natural lifespan is no guarantee of a natural life. Gary now faces the prospect of having to depend for his most basic needs on other people, primarily his parents.
We haven't spoke about it, my husband and I, but I think a lot. And I realised that if Gary is unable to do anything for himself, then I'm going to have to do it for him. And I think I'll be able to cope with it.
Do you think he will be able to cope?
Now, this I don't know, because Gary is independent.
The loss of independence is hard for patients to accept. Preparing Gary and others like him for a life in a wheelchair is the goal of care at Stoke Mandeville. While some doctors are beginning to talk of a cure for paralysis, doctors at Stoke Mandeville are unconvinced.
Well, I don't think there is talk of a cure. There's talk of hope of a cure. Patients recover spontaneously in our hands, in other people's hands. That's because the injury was less than total. And with that, you know, one can't disagree. There is no cure available today.
The work at Stoke Mandeville is typical of the traditional approach to spinal cord injuries. They believe that the unlikely recovery from paralysis can only result from the body's natural healing process. But what causes paralysis? What happens when the spinal cord is damaged? The spinal cord is the cable that conducts all messages to and from the brain. It is a continuation of the brain tissue, 18 inches long and 1/2 inch thick. The spinal cord is protected by 29 vertebrae, forming the spinal column. From 31 sites on either side, bundles of nerve fibers begin branching out. Each bundle contains hundreds of other bundles. At the core of each nerve fiber is the axon, which is responsible for carrying the electrochemical signals away from the brain to every millimeter of skin, every muscle, every blood vessel, every part of the body from tip to toe. Imagine if one vertebrae were crushed, one nerve bundle short-circuited and unable to get its messages. Thousands, if not millions of connections would be lost.
With the gunshot.
Miami, Florida is home to one of the 3 largest acute care centers for spinal cord injuries in the United States. Accident victims brought to Jackson Memorial Hospital have the chance to receive some of the most innovative and comprehensive care available anywhere in the world. The trauma team sees more spinal cord injuries in a week than most hospitals see in a year. Specially trained paramedics have learned ways to transport patients without aggravating their injuries. The philosophy here encompasses some radical and aggressive approaches. Almost half of the patients qualify for immediate surgery to relieve pressure on the spinal cord and to reposition the spinal column to its proper alignment. Jerry DeLapp, age 22, broke his neck when he dove into shallow water. Unlike Gary Byrne, Jerry was immediately airlifted to Jackson Memorial, and within 20 minutes, surgeon Barth Green was operating on his fracture.
In spite of the fact that all the medical literature reports that these people never recover, 1 hour after we realigned his spinal canal, he began to feel below his neck. He got sensation back. About 7 days later, he began to show a little movement in his toes, and today he has significant movement in his lower extremities, and in my estimation, he will end up walking. Now, in my opinion, if he did not arrive here as quickly as he did, and if this intervention was not carried out, that he would still be without sensation or movement.
Dr. Green and his team have developed a unique approach. Each patient receives a totally integrated treatment plan, beginning the moment they enter the emergency room and continuing the rest of their lives. The decision to operate in these first critical moments is not an easy one, but the goal of surgery is to stabilize the position of the spinal column early and to return it to as normal a position as possible. At the same time, efforts are made to reduce swelling, hemorrhaging, and shock.
Sir, do you know what happened to you?
The philosophy here is to make patients mobile as soon as possible. After emergency treatment, they are placed in rocking beds like this one, which fool the body into believing it's moving. This prevents additional complications like blood clots, bed sores, and pneumonia. Each person's individualized treatment plan is aimed at getting them out of bed and into active physical therapy in the first week.
We're one of the largest spinal cord injury care centers in the world, and every week we have new injuries arrive here at this center. And several times during the course of seeing these patients every month, I have to tell a patient that there is very little chance that by natural means that they're going to walk again. And unless I genuinely felt there was some hope for the future, it would be very difficult for me to cope with this situation. And I need this hope, and right now the hope is more than hope. It's based on concrete scientific information. So what I do tell them is, by natural means, there's little chance that you may walk again, but there is hope through research.
Jackson Memorial Hospital has made a strong commitment to develop new treatments and to look for a cure for paralysis. Taking advantage of new laser technology, researchers are exploring more effective ways to do surgery. Using rats, they're experimenting with lasers as a substitute for stitches when operating on tiny nerve fibers. These lasers weld the fibers together, eliminating scar tissue. They are also testing the possibility of reducing or preventing the onset of paralysis through the injection of a naturally occurring hormone. Thyrotropin-releasing hormone, TRH, was first used to treat spinal cord injuries by Dr. Alan Phaeton. This represents a totally new approach to confronting paralysis. After a spinal cord injury, the body releases endorphins to inhibit pain, but a side effect of these hormones is further damage to the injured area. It now seems that some of the paralysis following spinal cord damage is the result of the body's own biochemical activity. The hope is that TRH can limit the production of these endorphins and perhaps curb paralysis. At another research center, New York University Medical Center, researchers are trying to figure out what biological processes cause paralysis. They want to understand both what happens to the nerve cell after injury and to uncover how many nerve fibers must be damaged before signals from the brain are no longer received. Through electrical stimulation of the individual nerve fibers, they've been able to measure the extent of the nerve cell damage.
Of course, most spinal injuries that occur as a result of a fracture of the spine, that the two pieces of bone separate and move relative to each other so that the spinal cord is pinched very suddenly by this break. This is a very uncontrolled and very variable injury. And so in order to model the most central part of that, what we have to do is to expose the spinal cord by removing the upper crest of the spine and then apply a brief mechanical impulse to the spinal cord. And the method of choice, which has been used now since 1911, is to drop a weight, which uses the force of gravity as a standardizing influence.
For each experiment to be replicable, the spinal cord must be damaged in the same manner.
Okay.
With selected cats, the cord is removed and examined. They are looking to see whether the nerve cells die and don't work, or remain alive but lose their ability to function. So far, they have found that if at least a small proportion of the spinal cord remains undamaged, then the cats can recover some of the sensation in their hind legs, enough to stand and scratch. In a related series of experiments, they're beginning to challenge current beliefs about how long it takes after an injury for paralysis to occur. Are they close to understanding what happens in the first critical moments after an accident?
I think we're close in terms of defining most of the major events within the first 3 hours. We have an idea of what is happening between 3 hours and 24 hours in terms of the neurophysiological changes. We have some inkling of what is happening at 1 week. Beyond that, we don't know. The dogma is that the injury is over with and finished. Nothing more happens in the spinal cord after the first 3 to 24 hours. Therefore, there's no point in looking at.
Do you believe that's true?
No.
The human embryo. Researchers are continually learning about how the body works and how life begins. Yet a fundamental biological puzzle remains. Why is it that during the development of the embryo, central nervous system cells grow, but at birth, they stop? In the last 10 years, some radical new discoveries have shed light on this mystery. Dr. Jeffrey Raceman and his team at Britain's National Institute of Medical Research were one of the first to make a significant contribution to the field of nerve cell regeneration. Their focus is on why, once damaged, central nervous system cells don't reconnect with each other. They have grafted cells from unborn rats, cells that still retain the potential for growth, into adult rats. Their hope was that the fetal cell would graft onto the host cells and grow. They then examined the edges of the graft to see what happened. They collected the information, plotted it out, and in 1982, Dr. Raceman found some connections, but he is realistic about the success of this experiment.
Although what we have done in the rat is very exciting to us and took us a lot of effort, it's still a very long way from having any human application. It's a particle of the knowledge which in the end we hope will have a bearing on it, but it isn't all of it. It's no more all of it than if you wanted me to build a cathedral and here I am standing with one brick in my hand, it may be made of bricks if it's a brick cathedral, but I can only put in one at a time. I can't build the whole thing at one go. It has to be a collaborative effort. This is our little brick, and the building's a very big one and a very complex one.
Another researcher also working with embryonic rat cells is Dr. Jerrold Bernstein. His experiments involve grafting fetal spinal cord tissue into the adult spinal cord.
One of the things that I've been working at for almost 25 years is to see if there is some way that we can get the chronic spinal cord, injured spinal cord, to regrow. Since 1970, I have really been convinced that it is possible.
After getting the transplanted nerve fibers to grow, he is now trying to direct these fibers to grow across the damaged area.
Maybe there's a mechanism by which we will be able to introduce one, new cells, so you have a new source of nerve fibers as well as new cells, and we make a little lesion in the coverings of the spinal cord and put this fetal spinal cord on the top. And let me show you some of the things that we find when we do this. What we have here is a cell that's, you can see, has two very, very intense blue dots. And that is a nerve cell that has two nuclei. And it is a cell that is a fetal cell that has recently divided. So now what we're finding with these transplants is that these nerve cells do indeed grow into the spinal cord.
Despite Dr. Bernstein's recent success, he believes that the practical applications of such basic research are still a long way off. Dr. Albert Aguayo of McGill University has taken another approach. Scientists have known for some time that nerve cells outside the brain and spinal cord can grow. It's the nerve fibers in the peripheral nervous system which carry messages to the extremities that can reconnect and regain normal functioning. Dr. Aguayo's research focuses on the sheaths or coverings of the nerve fibers. He believes it to be the particular covering that accounts for the growth of the peripheral nerve fibers and inhibits the growth in fibers of the central nervous system. Given that, Aguayo has been experimenting with transplants of the cells that normally enclose the peripheral nerve fibers. He grafted these into the spinal cord of the rat, trying to encourage the damaged cord to use the sheath and grow through it. The experiments have been successful, but problems still remain. How can he get the nerve cells to reconnect and reconnect correctly? So far, the nerve fibers have penetrated only a few millimeters, and then they have come to a full stop. Nor is there evidence that this penetration has restored any function, any movement to the rats with a damaged spinal cord. Dr. Aguayo is understandably cautious.
And to be realistic in this moment means that all what we know is that some nerve cells can grow long processes that can reach regions that are situated far apart, far away from the source. And that is all what is real. The rest is all hopes and plans.
But even if the central nervous system tissue is persuaded to link up again, how will scientists prove that it has done so, or that the links are between the correct nerve fibers and in the correct proportion? Here in the Department of Neuropathology at Harvard Medical School, researchers are examining those questions. This three-dimensional picture of a single nerve cell has been generated in the Image Graphics Laboratory. Advanced computer technology gives these researchers an invaluable visual representation of the complexity of rewiring a nervous system. Professor Richard Sidman and his team have been trying to make order out of this apparent chaos. By examining how the peripheral nerve cell of a mouse grows, Professor Sidman has been looking for ways to help the body heal itself.
Nerve fibers grow essentially through activity at the tip of the growing fiber. The tip seems to sense its local environment, and the growing tip of the nerve fiber makes physical contact with solid surfaces in its environment, and it crawls along them. A nerve fiber doesn't swim the way, say, a tadpole moves through water. It crawls along solid surfaces. Those surfaces are not available in the adult.
From this unique time-lapse photograph of an embryonic mouse brain cell, we can clearly see the development and extension of the fiber's tip as it grows along the top of a solid surface.
Our reasoning has been then, let's try to substitute in the adult an equivalent set of surfaces for nerve fibers to crawl along.
He's been making pathways to guide the reluctant nerve fibers to their proper targets on the other side of the gap in the nervous system. He's designed small tubes made of a variety of molecular compounds that occur naturally in the body. First, he tried to reconnect nerve fibers in the peripheral nervous system of a mouse, and it worked. This historic photograph shows the reconnection of a peripheral nerve. The tube has disappeared, absorbed by the body. For Professor Sidman's team, the next challenge was to move on to the central nervous system, the spinal cord. They gave a mouse an anesthetic, then cut the animal's spinal cord. They wanted to equate the wound with a spine that had been shattered by a bullet. They prepared a variety of polymers because some tubes proved poisonous and others weren't absorbed by the body.
We insert at the site of injury a segment of plastic tubing oriented lengthwise along the main axis of the spinal cord. We then close the coverings around the spinal cord and let the animal recover from anesthesia. At that point, the animal's legs are paralyzed because its spinal cord has been cut. And then we watch to see over the ensuing weeks and few months whether behavioral recovery occurs, whether the mouse will walk again, whether it has sensation in its limbs. If we had been entirely rational in our approach to this work, we wouldn't have gone near the central nervous system yet, because we have so much to learn about this new system, even in the peripheral nervous system of the mouse. But we're humans, and we couldn't resist the temptation to make an attempt to leapfrog and get a result in the central nervous system. That is, after all, the aim for all of us in the long run. And we have made such attempts.
All those attempts to date have been negative. Not a single nerve fiber in the mouse's spinal cord has grown. But Dr. Sidman and his team were undiscouraged. One team member, Dr. Roger Madison, has turned from the spinal cord to a less complex part of the central nervous system, the optic nerve. The optic nerve has proved to be a more successful test case for nerve cell regeneration. Here in the center of the screen, the white fiber marked by the black arrow is the optic nerve. After exposing it, the researcher cuts it in two. In the upper half of the frame, marked by two arrows, is the damaged optic nerve. A transparent tube designed to create an environment conducive to growth is used to enclose the two ends of the nerve. Note the shiny area in the middle of the screen. In the center of the screen, the polymer, the white mass, is beginning to dissolve after 1 month. Preliminary results show central nervous system cell growth inside the tube, but no connections have been made. No function has of yet been restored.
I feel that something has happened to them that they didn't ask for, that came out of the blue in most cases, totally changed the direction of that life, and that it is incumbent on all of us as fellow human beings to try to do something serious for them.
I think that it is important not to raise false hopes in people. And it is important for people to understand that these are very complex issues.
Janet Reed, like most of us, never gave much thought to paralysis. 5 years ago, her passion was riding horses.
November 17th, 1977, the beautiful day, I went out riding to hounds, and everything was going quite well, and I thought that day, gee, how great it is to be alive and how well my life was going, and everything was just perfect. Just one of those feelings. Then 10 minutes later, my horse went into a jump. He missed the jump in a sense that his hoofs hit the jump. It flipped him over. It tossed me in the air. I seemed to be in the air for forever. I landed, and when I landed, I hurt terribly. My whole chest felt like it had collapsed. I have not come to terms. I will never come to terms with the fact that I was told I will never walk again. I am fighting it. I am looking for a cure. I'm doing what I can. I'm devoting my energy, my time to help raise money to fund research that hopefully will lead to a cure.
Good afternoon, American Paralysis Association.
This organization is just one of several small nonprofit groups trying to find a cure for spinal cord injury. Other organizations, like the National Spinal Cord Injury Association, raise money not only for a cure, but also for rehabilitation programs.
Bye.
And have you had any word from Jerry Landreth yet concerning
Kent
Rich
Waldrop,
Little?
president of the American Paralysis Association, spends many hours a day on the telephone organizing events and raising money.
Headliner next year at our Washington Gala. It's a situation that we face in the private sector, that there's never been a national organization that has devoted itself to the problem of curing spinal cord injury. There's never been the American Cancer Society of Spinal Cord Injury, the American Heart Association, the Muscular Dystrophy Association. We haven't had that. We haven't had that focused effort of raising the millions of dollars, the tens of millions of dollars that are needed to fund the research.
The APA's efforts are twofold: raising money and disseminating the funds. Research Vice President Admiral Richard Van Orden has the job of assessing all the different research programs. Today, he's in Great Britain at Leeds General Hospital to meet Dr. David Wilson.
What I'd like to know, Dr. Wilson, is how does this machine operate? Can you explain the diapulse techniques?
Yes, well, the machine is simply a pulsed radio frequency generator.
This machine transmits electromagnetic energy. The machine is commonly used to speed up the recovery of patients with broken bones and sprains. The same machine is also used to treat similar ailments in the United States. Impressed with its capabilities, Dr. Wilson began to use the machine to treat cats with damaged spinal cords.
Treat them 2 or even 3 times a day.
He removed a portion of the spinal cord, replaced it with a graft of the peripheral nervous system tissue, and waited to see whether the cats would walk again. When treated with a diapulse machine, says Dr. Wilson, the cats recovered far more quickly.
Clearly, we have demonstrated regrowth in the central nervous system.
Well, Dr. Wilson, Others would say, of course, that they have seen no evidence of the growth of central nervous system tissue and the restoration of function.
Well, I'm aware of that. Of course, I was teaching the same thing until 5 or 6 years ago. But now, not only my work, but other work in other places in the world, I think, have supported the, if you like, revolutionary idea that the central nervous system will regenerate or will recover under favorable circumstances.
And you believe that?
Yes, well, it's no longer, for me, it's no longer a matter of belief. It's a matter of having seen it and being proved.
But Dr. Wilson's research has been challenged. Critics assert the cat's movements could have been restored because the spinal cord was never fully severed. He is eager to counter those attacks and further his research.
My plan now is to do this work in monkeys because they are bipeds. They stand on their back legs like human beings do, and they are the nearest example to a human being that we can get for an experimental animal. And if it's successful in monkeys, then I would feel that one would be justified in using this experimental technique on patients.
Even though this time Dr. Wilson's research did not meet with approval, the APA is determined to find other research projects they can fund.
Our program is unique to any other charity in this country because of one central theme: the fact that we're in business to put ourselves out of business. I don't want to be doing what I'm doing now 10 years from now, and I don't believe I will be, because I believe that I'll be doing something else, and that something else will be done out of a wheelchair.
Nova asked Janet Reed, wouldn't the money be better spent improving the lives of those in wheelchairs?
I certainly don't think so. And there's many millions of people who would certainly agree with me. First of all, it's not cost effective to the economy. The economy here is something like $6 billion a year to maintain the agony of paralyzed people, people with various illnesses. It's a big business. Now, from that standpoint, it's very profitable. But from the standpoint of someone like myself who's in pain and agony, it certainly is not what I want. And it's not what's good for me.
And you're not prepared to settle for that?
Of course not. Why would anyone want to settle for the condition I'm in, to feel the chronic pain I'm constantly faced, the discomfort, the mental anguish, the physical pain, the whole thing, the loss of my quality of life is just, it's incalculable. There is no dollar amount you can put on it. So don't tell me about rehabilitation, and that's the answer.
There's a lot of confusion today about what a cure is. And I think in order to understand this, you have to look at the problem. Our problem is twofold. One is to get people up out of their wheelchairs walking, but a second is to make them as normal as possible, as close to what they were before they were paralyzed. The first goal, to get people up out of their chairs walking, is a reality today.
Dr. Bernard Brucker directs the University of Miami Biofeedback Laboratory. Here he has developed a system to teach spinal cord injured people how to learn control over their physiological responses.
Biofeedback is a learning technique, very similar to the type of trial and error learning that we're all very familiar with, that accounts for learning to walk, drive a car, play the piano, play basketball. Dean, with this system, it's a matter of this computer that measures the signals that comes from your brain down to these various muscle sites, past that part of the cord that has the injury.
Dean Rose is paralyzed in both his arms and legs. He is beginning the first of a series of 8 45-minute sessions. He must concentrate intensely to direct a neurosignal to a specific muscle in his arm. Brucker knows that it works, but he isn't exactly sure how. The theory is that the person learns how to create a new pathway through the spinal cord, probably by sending messages to those cells still undamaged. But this only happens if enough healthy cells remain after the injury.
Responding well, the triceps not responding at all, and the biceps just responding very partially. To see exactly how many signals are getting through, that's really the first step. These electrodes that we put on don't give you any stimulation at all. We put them right over the belly of the muscle like so, and what happens is they read the signals that come actually from your brain down to that muscle ending. And within a few seconds, you'll be able to see the responses right there on the screen. Okay, Dean, let's just bring up that signal on the top part of the screen. Just bring it up for me. Good, 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 Very nice. Very nice. See what's happening?
I see that we're getting a steady increase here, but just how exactly is that coming about?
We never really know exactly what happens neurologically when we learn something, but we know if we set the conditions for learning properly, that people can learn very fine control in terms of coordination.
The response on the screen is the feedback to the patient, letting him know he has learned something. Without the screen, there is no other way for him to know he's accomplished his task.
Here, the important thing is that these changes that occur are so small at first that you would be unlikely to detect them or be able to know how well you're doing on a particular try unless you're able to see them or get some meaningful feedback on what's happening. That's how this system works.
That the system works at all goes against accepted theory. Bill Heller is one of Dr. Brucker's early success stories. When he began working with Dr. Brucker 2 months after his motorcycle accident, he had been diagnosed as completely paralyzed. But after 10 sessions, he was standing and walking.
Very nice.
I started working over here on the biofeedback program with Dr. Brucker, and the improvement we noticed from session to session was tremendous. And following one session and coming back for another session, I wasn't losing any of my return. As a result of that, I'm looking forward to someday starting to lead a normal life and walking and carrying on as I did before I was hurt.
Biofeedback training has turned Bill's life around. Since this filming, he has abandoned the walker and now uses only a cane. But there are many others whose injuries are more severe, and for them, biofeedback won't work. For these people, hope may come from the new field of functional electronic stimulation. 2 years ago, Greg Kramer was offered an outside chance of walking again. He went to join the research program at Wright State University in Dayton, Ohio. This is a computer-based program, and it's an engineer's solution. Dr. Jerrold Petrofsky heads the program. For 13 years, he's been developing a system for bypassing the damage in the spinal cord in attempts to restore functional movement.
We've developed experimentally an active physical therapy program. It's a program whereby we can take people who are thought to be hopeless, people who have been in wheelchairs for 5 or 10 years, who have had deteriorated bone, muscle, heart, every other part of their body. And we can bring these folks, at least in the laboratory, back to health again. We can bring the muscle and the bone back.
Petrofsky has tried to perfect the equipment that would prevent the bones of paralyzed patients from becoming brittle and the muscles from wasting away. Using electrodes, he linked up the patient's body to his computers. He now had a link between the computer and the body's muscles, and he could control those muscles. He modified an ordinary exercise bicycle. He tried to fathom the sequence of signals sent out by the brain to the body in order to produce a given movement, in this case pedaling. Then he set out to reproduce that sequence and fed it into his computers. The computer would be the guide. He was making an electronic nervous system.
Okay, rotate. That's what I got. Rotate.
On April 28, 1982, Jeff Hausch, a quadriplegic, pedaled the bicycle.
Directly, the energy to move comes from eating, from food. They're using their own muscles. Essentially, what we're doing is the same thing as an artificial arm again, but in this case, they're using real limbs for movement, and the energy for movement, the strength, comes from metabolism, from glucose, fats, proteins, like any other movement. See how much smoother the movement is with that program statement change? All we're doing is causing those muscles to activate with electricity. It takes very small amounts of electricity to cause a nerve to fire and to cause a muscle to activate.
Yeah, he's doing 20K.
That was the iliacs. I'll bring back the gastroc a little bit. So another problem you have is associated with the heart. The heart really isn't in any type of condition to stand that type of stress. It's like laying in bed for 6 months and getting up and trying to run a marathon. Quadriplegics can't sweat. They can sweat on their head, but sweat's controlled by the sympathetic nervous system.
130 over 100.
So what we're trying to find out is how much heat they can dissipate as a function of the level of the injury in the spinal cord and what we can do about it.
125 over 95.
I've had federal agencies tell me that, going back as much as 3 years ago, that what I had in mind was preposterous, that people should get used to sitting in wheelchairs, and they're never going to get out of wheelchairs. Even many of the spinal cord societies, the different spinal cord groups in this country, stated as much as a year ago that, well, it'll be 20, 30 years before electronics get sophisticated enough, before you can get somebody actually having a coordinated movement. But we think it's fascinating what you're doing in terms of developing an electrical muscle trainer to try to help people stay in shape before a cure for spinal injury is found.
Microprocessors are programmed to imitate the brain. The sensors feed the information to the microprocessors, which send electrical impulses, making the muscles contract. This requires fine calibration to make the contraction precisely right. The position sensors tell the computer what the angle of the step is. The contact sensors let the computer know when the foot has touched the ground.
I was in a car accident when I was 18 on graduation night. We were on a narrow country road, and we rolled the Volkswagen down into a ditch. And I broke my back, and I broke my neck, and I was in the hospital 6 months. It was hard to take at first. Of course, I was depressed about it. But then you realize you got to go on. You can't let something like that get in your way. You can't stop living.
Nan Davis has been working with Dr. Petrofsky since her freshman year of college.
Fairly dry, they look very wet. We're not going to be ready to stimulate for a couple of minutes anyway, and then we want to check the individual muscles, and then we'll watch them at the time.
Working out on the exercise bicycle is part of Nan's program. Even the simple act of pedaling involves an incredibly complex communication between many nerves and muscles. Analyzing the sequences accurately has been a difficult task.
It's very smooth rotation.
It's working, though. It's working. There we go.
I always knew science would have it come up with a cure. I always knew they would. I never lost that hope. And they're doing it now.
Okay, we got it. It works.
The big day came for Nan on July 26, 1982. Dr. Petrofsky decided she was ready to try riding on campus using her own muscle power. After this success, Nova asked Dr. Petrofsky what is coming next.
Walking. The only reason we haven't tried it to this point, we have the electronics built for it. The only reason the lab hasn't tried it as yet is simply we're waiting for the limbs to be built back up again. When our population of subjects have large enough muscles and their bones are built up to a point where the team and myself feel that they can support their body weight, rather than pedaling a bicycle, we'll use the same type of control program to try to get them to walk. And the people, they know roughly the sequence of who we're going to try it on first also. Actually, there's a lot of competition in the group in the lab. They go back to the dormitory at night and compare notes on who pedaled the bicycle the longest. And there's always a lot of dissatisfaction and booing and hissing if somebody beats their time. And everybody likes to pedal the longest on the bike, and every week they're doubling their endurance time on the bicycle. And there's a tremendous amount of competition. And also they know that the ones who are in the best shape will be the ones we try walking first on.
Nan Davis, paralyzed for 4 years, was chosen to be the first. Petrofsky and his assistants spent over 2 hours attaching the myriad of wires and connections to their proper places. On the evening of November 10, 1982, they were ready privately to test the new equipment.
At 7 o'clock in the evening, I turned the power on, called in the programs, and she stood up. We tried that for a while, had her sit down, then we had her stand up the second time and walk. Power on. The thing we hadn't anticipated was that the person is a person. They're not a piece of computer hardware. And when we tried to have Nan walk the first time, it was a complete disaster. She couldn't coordinate her thoughts with what the computer was thinking about. So she had to learn how to stand and walk once again. That when I first turned the computer on and said, "Okay, Nan, stand up," she forgot how to stand up because it's been so many years since she stood up out of that wheelchair of hers. Left knee's not locked. No. That should lock it. There it is. Okay. She forgot how to move her body forward and change her center of gravity. So now she has to learn, just like a 1-year-old would learn how to walk. She has to learn how to walk and balance herself all over again. Watch it. Power's down, power's down, power's down. Push it back.
We know what it means to Nan to walk. What does it mean to you that she walked?
Well, it means that after 13 years, I know that my research works. It's something you never really knew in the past. Spending year after year after year working on a project, you always hope that your research is going to work. It's like the people trying to find a cure for cancer. If you spend your whole life on something, you never know if you're going to find the cure for cancer. But then suddenly, when you get a glimpse of the future and something really works in an experiment, so you know you can go on, that you are on the right track. It's just a very nice feeling.
First with the news, this is 22 Alive, the early edition. Tom Hamlin with sports and Janet McGill with the weather scene forecast. Now, Marcia Bonhart and Carl Day.
Well, thanks for being with us. The focus of the world and the nation on Wright State University this morning. 22-year-old Nan Davis became the first paraplegic to walk under her own power. 22 Alive's Norm West was there while history was being made.
Okay, ready? Okay, right leg coming up. That's good, man. Okay, left leg coming up.
They're crude steps to be sure, but for Nan Davis and a few million other wheelchair-bound people in the world, these steps represent the hope of normal walking someday in the near future. Wright State biomedical researcher Dr. Jerrold Petrofsky has been looking forward to this day for 13 years as proof that computer-controlled electrical stimulation can make muscles come back to life.
When she walked, she looked like she was carrying her own telephone switchboard. She had a great deal of wiring connected to her, and that wiring was a whole myriad of sensors from different parts of her body and electrodes to stimulate the muscle. That's a prototype. That's extremely crude, but it's a crude prototype. It tells us anytime you build something, you start big and you miniaturize it down. The next generation system, which will be the type that we'll be using for final, I think, permanent use, will have small processor chips, small pieces of silicon like sand from the beach. How big? No, much bigger than this. Okay, this particular integrated circuit, this is a large-scale integrated circuit, has about 30,000 transistors on it in the center. And these small chips will be on the different joints. Initially, we'll put them on the surface of the skin. That way you can change parts if you don't like what you have. They'll be just on the outside of the skin. There'll be one wire going down each leg, and data will be transmitted the same way you transmit data over a TV antenna. High-speed digital data from the belt with the small microprocessor up and down the leg with one wire instead of the myriad of wires that are there now. When we pass that stage, where we know we can have somebody walk with the small miniature chips and do it not only well, but safely, so that if they go onto ice or gravel or sand, they can still walk and maintain balance. Then we go to surgery and implant everything inside the body.
Less than 1 year away from the prototype equipment, Dr. Petrofsky had miniaturized and refined the system enough to remove the braces.
Right leg forward, here goes. That's good.
Although Petrofsky was the pioneer, he is no longer alone in the field of functional electronic stimulation. In the fall of 1983, Nova went to Wales, England, to record the work of Dr. Hugh Grenfell. Using techniques similar to Petrofsky's, Grenfell is attempting to create simpler and more accessible walking systems.
Well, I suppose really what we've tried to do is to go to a device as quickly as possible that Jan could use, actually for standing and walking, without having to do a tremendous amount of background research. No doubt the work that Dr. Petrofsky is doing obviously is going to achieve a far superior end result by the time he finishes all his work. But we felt that we could tackle it this way and get to something which could actually be used very quickly. And that was our target.
I think I've some secret arrangement about it.
Grenfell's system gives the user ultimate control over the computer through a series of hand switches, but maintaining balance is still a concern. In spite of the rain, Jan Burgess and Dr. Grenfell were determined to demonstrate the system for Nova, so Jan attempted her first walk on wet grass.
Right. Ready? That's better.
Yes, okay.
No, spider.
When Hugh first suggested that he might be able to stimulate my legs, I thought it was quite a joke, really. I had thought of sort of electronic trousers or something like this. But as far as walking with my muscles, I really hadn't considered that. I was quite willing to try, anything. And it just seemed to work. It was very good right from the start.
There's a lump there.
I can see you trying to avoid it.
The balance is the hardest thing. Everything else is manual and a little bit machine-like. But the balance is really the hardest thing that there is.
Go on, you're doing quite well.
You can see that from when children start to learn to walk.
It slid on the bag.
They've got the idea of how to move, and it's getting it all together in a balanced sort of way that's the difficult part.
Yes, there's an up bit.
Of course, the trouble is you veer to the left.
I don't think anybody can say where it will end. I think to go on holiday without a chair, that would be your wildest dream, so you could rush up the steps of the plane and sit in the back seat and then get off the other end and walk into the hotel, not worrying if the doors were 3'2" or the loo doors opened sufficiently to get in. This will be my wildest dream.
The simplified and direct approach taken by Dr. Grenfell dramatically expands the promise of functional electronic stimulation. For the thousands of people confined to wheelchairs, the future holds a promise never before thought possible. Science has opened a door once believed closed and is actively trying to find a cure for spinal cord injuries.
The work is not yet terribly visible to the biomedical community as a whole, and very properly not yet of importance to the practicing physician, because we're a long ways from providing new leads for the practicing physician or for the patient. But I think we can see that future coming.
If you look at the work across the world in neuroregeneration and general spinal cord research, I don't think anybody in a wheelchair should just sit there thinking, I'll never walk again. There is hope.
By June of 1983, Dr. Petrofsky had reduced the amount of equipment so it could be carried in a school bag. And with the eyes of the world upon her, Nan Davis walked to deliver her graduation speech.
Okay, stop here.
My feet aren't straight now.
That's all right. Don?
I'm tired. I'm not straight.
Okay. Don. Jan. Yeah, put a leg over with you. You straight yet? Okay, just stand here. Stay behind. Okay, there you go.
Guys. This is a special day for all of us. Everyone who is graduating has worked hard for this moment. And what makes it more special to me is the fact that this is the first time I've walked outside of Dr. Petrofsky's lab since my graduation night from high school. Thank you, Dr. Petrofsky. I know a lot of attention has been paid to me for my participation in Dr. Petrofsky's research project, but we're all in this. All of us have had our triumphs and our setbacks over the years. We have all worked hard to be where we are today, and I would like to congratulate you all. And I would like to thank all the faculty members throughout this university whose research may not have received the attention that it should, but whose persistence and education are the most important service to humanity. I'm proud to be one of the 1,300 students graduating today from Wright State University. Thank you all, and congratulations.
The material on this video cassette is protected by copyright. It is for private use only, and any other use, including copying, reproducing, or performance in public, in whole or in part, is prohibited by law.